Examples of Malus's law in classical physics and quantum mechanics. Bridging classical and quantum worlds. Video number 1 of 2. Malus's law states that the intensity of light I passing through a polarizer is equal to the initial intensity I0 multiplied by the square of the cosine of the angle between the light's polarization direction and the axis of the polarizer. The results of Malus's law are the same in classical and quantum physics in terms of the intensity of light passing through a polarizer. However, the underlying explanations are where things get interesting and weird in quantum physics. In classical physics, light is considered an electromagnetic wave. This means it consists of oscillating electric and magnetic fields that propagate through space. The direction of the electric field's oscillation is what we call the polarization of the light. Here's how Malus's law fits into this picture. When light passes through a polarizer, only the component of the light wave that aligns with the polarizer's axis is allowed to pass through. This process is called polarization. For example, let's calculate the component of the photon's 30 polarization that passes through the filter's 25 polarization. We use Malus's law. The photon's polarization direction equals 30. The polarizer's axis direction equals 25. First, we need the angle theta between the photon's polarization direction and the polarizer's axis. Since we are dealing with a single photon, we interpret I as the probability of the photon passing through the polarizer. The intensity I0 of a single photon is often taken as 1 for simplicity. Therefore, the probability P that the photon will pass through the polarizer is cosine squared of 5 degrees, approximately 0.9924. So, the probability almost equal to 0.9924, meaning about 99.24% of the photon's intensity will pass through the polarizer. Amplitude and intensity. The electric field's amplitude, height of the wave, is directly related to the light's intensity, brightness. When light passes through a polarizer, the amplitude of the electric field that aligns with the polarizer's axis is what contributes to the transmitted light. This is intuitive because we can visualize the electric field vector of the light wave. As the angle increases, less of the electric field vector aligns with the polarizer's axis, leading to a decrease in the transmitted light's intensity. When the angle is 90 degrees, the electric field is completely perpendicular to the polarizer's axis, and no light passes through. So, in classical physics, Malus's law gives us a straightforward way to understand how the intensity of light changes as it passes through a polarizer based on the alignment of the polarization direction and the polarizer's axis.